I've always believed that when one's doing history of science, one should not be presentist, but one should be Whig. By not being presentist, I mean one should understand one's subject in the context of the time, but by being Whig, I mean that one should believe that we now understand more about the subject than did scientists in the past. The Whig interpretation of history in mainstream historiography, the term is due to Butterfield, is that the world is getting better and better, and soon we will all live in a perfect liberal democracy. But perhaps in science we do advance. And indeed, the history of color science is very much a matter of conceptual development as much as experimental progress. And largely the elimination of category errors, of assigning a particular finding to the wrong domain of science. So that for a long time, the fact that you could produce all colors from 3, trichromacy, was assigned to physics rather than to the constitution of man, as Maxwell put it. So I'm going to take a rather unusual approach on this basis. I'm going to tell you about, a little bit about modern understanding of color vision and then go back to Maxwell so that we have a conceptual advantage. The view of the retina has changed in very recent years. You shouldn't imagine that the retina delivers to the brain a pixel by pixel representation of the image that's formed on the retina. Instead, there are something like 19 different types of preprocessor that tile the entire retina and extract different properties of the image, such as color, direction of motion, different spatial frequencies, temporal modulation, and so on. So these preprocessors are the output of the retina, the so-called ganglion cells, and there are at least 19 types of them. The light comes through all this machinery and is absorbed at the back of the eye in the rods and cones. There is nowadays a 5th photoreceptor in the eye, which is the only receptor that signals absolute light intensity, and these are melanopsin-containing ganglion cells. Some of the ganglion cells are themselves intrinsically light sensitive. But I'm going to be talking about cones today, which subserve our daylight vision. There are 3 kinds of cone. Their absorption curves are shown here. And their peaks are actually in the violet, in the yellow-green, in the green, and in the yellow-green. So the actual wavelengths of peak sensitivity are given here. These two are very close together and strongly overlap. So you can see there's no wavelength that uniquely excites one of these classes of receptor. So these 19 different kinds of preprocessor are extracting different properties of the image and sending them to the brain, to different places in the brain. There's nowhere, as far as we know, there's sort of an equivalent of a screen corresponding to our wonderful coherent image of the world. And some of them are extracting color, and I'll show you an example of one of those in a moment. To understand color vision, it's good to always refer back to what's been called the principle of univariance. Although the input to a cone can vary in wavelength or in intensity or frequency and quantum flux, the output varies in only one dimension. It's in fact the degree of electrical polarization of the cell. This means that cones themselves are colorblind individually. Once a photon's been absorbed, all information about its wavelength is lost. Because of this principle of universe, you can represent all lights in a very simple system. Maxwell realized this. It's a three-dimensional system. In some of his lectures, he spoke in the room about the three dimensions of the room. And any light is a vector that's within this space, represented by the photon catches of the three classes of receptor. Now, if you want just interesting color, you can erect a triangle here, and that's essentially what Maxwell did, so that you represent a particular colored light by where it passes through this triangle, and that essentially is representing the ratios of excitation of the three different kinds of receptor. So it's eliminating intensity and just representing the ratios of excitation in this plane. Now, you can see from the absorption curves that there's no wavelength that uniquely excites one class of cone. And the big question that I want to ask as we go through is how well Maxwell understood this. Much of the confusion in the history of color vision has come from people thinking that there were three receptors and they could be stimulated by corresponding physical lights. There aren't, but to find out about color, the retina needs circuits that compare the rate at which photons are being absorbed in different classes of cone. Let's have a look at one. This is a type of ganglion cell that's called the small bistratified type, one of these preprocessors in the retina. This is a little patch of photoreceptors. They exist in unequal numbers, so the shortwave ones are rare, but there's an intermediate kind of cell which collects signals from these short wavelength receptors, and that delivers an excitatory signal to this ganglion cell, and other intermediate cells deliver an inhibitory signal to the ganglion cell. And the ganglion cell effectively is extracting a ratio of excitation of the short wavelength cones against the other two. Now, it's obvious why the retina really has to do that. We can deal with 10 log units variation in light levels from a starlit road to a sunlit ski slope. You can't transmit to the brain reliable signals over that range using action potential nerve impulses. What's being done most of the time in the retina is the extraction of ratios of local levels of light, absorption, different cones, and so on. And it's the ratio signal that's transmitted to the brain. And this is what Maxwell didn't have available to understand. If one recorded from such a cell, one with monochromatic lights, different wavelengths, one would find that whatever the intensity, all short wavelength lights would excite this cell, and all long wavelength lights would inhibit them. It was known essentially by the 18th century that human vision was trichromatic. So a formal statement of the fact that you can produce all colors with three variables is this, that you can either place three of them on one side of a central matching field, falling just on the fovea of your retina, the central part, or you can place two of them on one side and two on the other, and by manipulating the intensities of three of them, you can cause the two sides of the field to match. That's a formal statement. There's some small print. it shouldn't be possible to match any one of the variable lights with the other two. This in the periphery of our vision, where there are other kinds of receptor, these melanopsin-containing ganglion cells and rods, the match may not hold, and there are some, possibly, women in our population who are tetrachromatic and have four types of cone in their retina. So now let's go back to Newton, because I want to discuss this really mischievous term, treacherous term, primaries, that has led to much of the confusion in the history of color science. So it's meant at least four different things. Newton used it just for monochromatic lights. It's been used and is still used to mean the wavelengths, and they're essentially arbitrary, that you use in a color mixing experiment, such as the one I was just describing. That's where you're mixing lights. It's sometimes used also for when you're referring to subtractive color mixing in painting or printing, where the rules are different from additive mixing of lights. And then again, it's used phenomenologically to refer to four colors, a red, a yellow, a green, and a blue, that to our eye are phenomenologically unmixed. So many people would agree that you can see redness and yellowness in orange, but in a pure yellow, you can only see one quality, and you can't subjectively divide it any further. These are our private sensations, and unfortunately, especially because we can't share them, people get adopt very strong views about this sense of primary. So these are pure hues, here, and here, and here, and here. What has been a source of much mischief is the mistaken assumption that the peak sensitivities of the receptors in the eye must correspond to one of these senses of primaries. Much of the confusion in the history of color science comes from that. And you may have been taught at school that there were red, green, and blue receptors in the eye. Now, Newton had, of course, his own color circle, and Maxwell and many people since have said that trichromatic mixing is intrinsic in Newton's color circle. Newton himself was much more guarded. He didn't really commit himself to saying you could produce all colors by mixing three. And he's very vague, of course, about what the center of gravity rule depends on. What are the units in which you hang weights on here? He just says numbers of rays. The reason that he didn't take this color circle further and be firm about trichromacy is that in his model of how the physiology of human beings, there weren't specific transducers for different wavelengths. So he supposed that the vibrations of the ether were directly transmitted along the optic nerve to the sensorium, a place where the soul had intercourse with the brain and sensations were aroused. So in this case, you can only put your primaries inside this space. But here we see him being explicit about this, his physiological model. He thinks that the vibrations are directly propagated along the nerves. What he didn't have the idea that came with Thomas Young of transducers that are tuned just to part of the spectrum. And once you have that idea, you can place them outside the color circle, and then by the relative activity of these three, you can represent any color within the color circle. Now, Thomas Young's theory that there were three transducers had been put forward in 1801 in a Bakerian lecture, but it had been much neglected, and there were still those who believed that there were three physical kinds of light. And here's a paper by a contemporary of Maxwell's, an older man, David Brewster, who dominated by bombast as much as by intellect the physical theory of light in Edinburgh when Maxwell was young. And he supposed that there was red light and yellow light and blue light, but they varied in their refrangibility. So you had these three spectra. So Maxwell adopted Thomas Young's idea that there were three kinds of transducer, and he projected this triangle, and this is his triangle. And in 1855, he had his imaginary primaries, that these transducers at, this is violet, this is green, and this is red, well outside the space of colors that you can actually produce. Now, interestingly, he gave a paper on color mixing demonstrating his top exactly 180 years ago this spring to this society. So we're honoring him at the right moment. So here, these are real colors, but the actual primaries, or the transducers, lie well outside, so you can't, with real colors, excite any of them. He's saying this fairly clearly here. Now, what he demonstrated to the Society 180 years ago was using his top, or a forerunner of it, and you can, when you spin it at speed, the colors are fused, but he showed that you get the same results as you could get by optically superposing them. And you can get an equation of what mixture of the three primaries, and he calls them standard colors, rather carefully when he's a young man. You can find which of these match to white. So here he is saying he's not going to call them primary, he's going to call them standard. And he had to deal with the people who mixed paints and knew that by mixing yellow and blue you could get green. And that's not true for mixing lights, of course. So let's look at one of his first equation. He's spinning his top, and the units in which, and this is treacherous, the units in which he's expressing the component colors are divisions of the top, and there are 100 divisions of the top. So this means 37 divisions of violet, 27 divisions of ultramarine, and 36 of emerald green match this white. This is a gray, of course. So to express in terms of these three standards, which he places here, the white, he has to find the center of gravity. And so A is the center of gravity of the amount of violet and of red and ultramarine. This is V is vermilion. And then you take the weight of those two in the equation and divide this line through the emerald green standard to get the position of the white, the grey, in this representation. Now, that's very straightforward, but he gets into a problem when he wants to locate in the diagram pale chrome yellow. This is my attempt at finding what pale chrome yellow would be, slightly reddish yellow. And the problem then is that he gets this equation where the amount of white, this is snow white, is different from in the last equation. And he avoids this in the color box, as we'll see later. So this means you need 33 divisions of pale chrome, 55 divisions of ultramarine, and 12 divisions of emerald green to make the match. Now, he has this problem that the match now is to a brighter white. It's 1.32 times as bright as in the first equation that I showed in the last slide. So he says, well, the left-hand side of the equation must be increased to give a total of 132 of these mysterious divisions. Well, ultramarine and emerald green is unchanged, so he's going to take the brightness, the intensity of pale chrome, to be 132, which has got to be to balance the equation, minus the two values from ultramarine and emerald green. And the essence of the problem here is that these divisions don't correspond either to the luminances of the lights or to their energies. They're absolutely arbitrary. And in a modern space, we would make, in a modern chromatistic space of this kind, we would make the positions of the colors dependent just on the ratios in which they excited the different kinds of transducers. But in Maxwell's case, what he's doing is making the valence of pale chrome depend both on the ratio in which it excites the different receptors and on its intensity. So he's limited. I mean, although you could measure wavelength very well in 1855, there were no estimates of luminance, and also he didn't attempt any physical measurements of intensity. However, despite this imperfection, he can make a circular check and check that chrome yellow is where it would be expected to be theoretically. So what he does here is he says, well, we'll now not have white and black in the middle. We'll mix pale chrome with ultramarine sorry, this is located, this is the previous one we want next. Ignore the text there, which is not the right text. He says, theoretically, we've located pale chrome here. if we mix the red, this vermilion, with emerald green, and with ultramarine and the pale chrome on the other side of the equation, it's got to fall at this point gamma, which is the only point where these cross. And we can do that equation. So instead of having white and black in the middle, we can have ultramarine and pale chrome in the middle, and then we can check whether this is in the right place. And he does those empirical checks, and they come out very well, so that the position of gamma on this axis is correct, and on this axis. Now, the problem that he had with luminance is eliminated with his color matching box, there are many versions of the color matching box in successive papers, and he already had one version of it in Cambridge. This is the version he used for his big paper. So white light is admitted along here. There's a board illuminated by sunlight out here. It's essentially a reverse spectroscope. So if you had a light source here instead of the eye, then these prisms would form a spectrum here. So because light is reversible, if you have a source here, an extended source here, you can pick off particular wavelengths and bring them to focus with this lens on the eye, and the eye sees an illuminated uniform area of whatever wavelengths you choose to pick off here. There are 3 slits, and he can adjust the intensity by varying the width of the slits. Now, there's a mirror here, it's run up here. So you see half the field illuminated by white light, and then you have to adjust the 3 variable wavelengths to make a match. His assistant, his collaborator and fellow observer in these experiments was his wife. Here they are. And here are some of his experiments. Now, to read this equation, you have to know that these are in the brackets are not quantities. These are positions of the slits in the color matching box. These are quantities, not in brackets. They represent the width of the slit, and thus its intensity, the intensity of that wavelength. It was not a toy. This was a rather precise instrument, and the results he got agree quite well with modern estimates from our knowledge of what the solar spectrum would have been. So then what he has to do, he's got this basic equation for his 3 standards, 24, 44, 68. These are a violet, a green, and a red. And then he moves one of the slits from 24 to position 28 and gets a second equation. Now, in this case, things are much easier because the white remains the same. So he can just, to re-express the new wavelength in terms of the standards, he can just subtract from the 2 equations and find the position of the new wavelength. So he can work through the spectrum expressing each wavelength in terms of the 3 standards, substituting the test wavelength for one of the standards. And now he gets chromaticity diagrams for himself and his wife that aren't like circles. The chosen primaries are here and here and here, and he finds that the spectrum really is like two sides of a triangle. But it's not quite the same for himself and his wife. There's Catherine, there's James. And he can express the results in another way, which nowadays we'd call color matching functions. And these are essentially correct. The spectrum is plotted backwards. So this is red here. So this is the amount of the red primary in the mix here, goes negative. This is the amount of the green primary, and this is the amount of the blue primary. And S is simply the sum in arbitrary units. And there are wavelengths which apparently are stimulating just single systems, let's say. There's a wavelength in the red where there's no excitation of this green curve. There's a wavelength here where there's no red excitation and only green excitation, and a wavelength in the blue similarly where it's just blue. And here he wants to explain why he gets slightly different results from his wife. And in the center of our vision, in the center of the retina, there's a yellow spot. It varies very much in optical density between people, and actually we now know it's the optical density is smaller in women on average than in men. Here's a low magnification image of the fovea of the retina, the central part. And this is its absorption spectrum. It peaks at about 460 nanometers. And we still, to this day, refer to the subjective appearance of this spot as Maxwell's spot. And he noticed that when he was looking at an extended spectrum, there was an area around 460 nanometers. These are Fraunhofer lines, where he saw a dark spot, and he demonstrated it by alternating between yellow and blue. But not everyone saw this, and he thought that this was a major source of variation between people. Now, this kind of variation, we now know that this is a source of variation, but another major source of variation is that the proteins that form the light-absorbing pigments in the cones are polymorphic, vary between people, and if you have normal color vision and you're male, then you have a 40% chance of having one amino acid at a critical position in the molecule and 60% of having another molecule, and that will shift your long-wave length receptor by 4 nanometers, producing variability. Now, real color blindness he was very interested in, and he got equations from colorblind observers. This is with the original top, so this means that a mixture of green and blue plus some black will match 100 divisions of pure red in the top. And he used different positions along this axis to triangulate as to where the missing receptor essentially would be. And this is a method that has been much used subsequently to locate in such a diagram the position of the missing fundamental. This is the portable apparatus, which I think is this one. where you make it shorter by reflecting the rays back to an eyepiece here. And these are color matching functions that you obtain for dichromats. And they're very reasonable color matching functions if converted with modern knowledge of what the solar spectrum is. He calibrated his instrument with great care for wavelength, putting interference plates at a source here. But did he really understand that there are no receptors that uniquely stimulate one class of cone, one class of receptor, no wavelengths that stimulate one class of receptor? When he was a young man, when he would have been speaking to this society, he was quite firm that every ray of the spectrum gives rise to all three sensations. And the beginning of his major paper with the color box, he says, well, we don't know whether any kinds of light have the power of exciting the primitive sensations separately. But then he lapses. These are the results I've shown you. And he says that all other colors of the spectrum may be produced by combinations of these three wavelengths, which correspond to a scarlet, a green, and a blue. And then he says, I have strong reason to believe that these are the three primary colors corresponding to the three modes of sensation in the organ of vision. And with his physiological model, that was sort of unescapable. So what was it that he didn't understand? What he didn't understand was that those wavelengths are not ones that excite single classes of receptor. They're ones that produce the maximal ratios of excitation of those receptors. And remember that it's the ratios that are being transmitted from the retina to the brain. So although there are no wavelengths that excite a single receptor, you can choose wavelengths out here that produce the highest possible ratios, and there's one here, would be in the bluish green, and one in the violet. And then you can match most colors with positive mixtures, although there will still be some that you have to move to the other side of the equation. So that was what Maxwell didn't understand. Using his method of estimating the fundamentals missing in different kinds of colorblind people, within a decade of his death, Arthur Koenig in Helmholtz's laboratory had produced estimates of the sensitivities of the receptors that are very close to the modern ones. Again, you have to read the spectrum this way. This is red. But these are quite close to modern estimates. You have to do it in terms of the solar spectrum, which they didn't have good measurements of. So it's been impressive to me to realize how far Maxwell took our conceptual understanding. He himself was limited by his own physiological model, where he thought that there were just three kinds of receptors that directly signaled to the brain. But I'd like to thank the Society for obliging me to read once more these great papers on color by Maxwell, which are so wonderful in their clarity of thought. Thank you.